Hi everyone, I'm Dan Fullerton, and in today's lesson we're going to talk about elevators. Our objectives include utilizing free body diagrams to identify the forces exerted on an object, write and solve Newton's second law equations corresponding to given free body diagrams or pseudo free body diagrams, and to predict the motion of an object due to multiple forces by applying Newton's second law of motion. And elevators make a great vehicle for practicing this. So, first thing we need to talk about is what scales do. Scales don't really read mass or weight. Even if your scale reads in kilograms, it can't measure your mass. What it's actually measuring is the normal force exerted by the scale back up on you. So if we were to draw a diagram of this, let's put our scale down here on the ground somewhere. It has probably a little bit of a window there, and we've got somebody standing on top of it. So if that's our scale, and we're going to draw a free body diagram for the person, it'd probably look something like this. There's our person. We have the normal force pointing up, or the force of the scale, and the weight of the person, assuming we're on the surface of the Earth where the gravitational field is relatively constant, or the surface of some other planet, mg. That's our free body diagram for somebody standing on a scale in an elevator. And physicists really love these types of problems because it's a great way to practice Newton's second law. Let's take a look and see what happens when we actually go and do this on an elevator.
All right, so I'm in the elevator. I'm going to stand on the scale, and we should see that the mass of Mr. Fullerton is roughly, let's see if we can zoom in there and get something a little clearer, right around 200 pounds, 93 kilograms or so it says. That sounds about right. All right, so let's see what happens when we adjust this a little bit. I'm going to hit the button on the elevator and we're going to go up. What happened there? Now as we go up, we're traveling up at constant velocity. In a second, we're going to slow down and stop at our highest point. Oh, what did it do there? It was lighter for a second. The door opens, and let's try going down now. We're at the highest floor. I push the ground floor button. Let's see what happens when we start moving. Reads 2. Reads less for a second, back to 200, as we're traveling at constant velocity. And let's see what happens when we get to the ground floor and slow down and come to a stop. It reads heavier for a second. I wonder why. We'll come to a stop here in a second. And we're just above 200 again. Once more, let's ride the elevator to the top. Doors closing. Accelerate upwards. Now we're traveling upwards at a constant velocity again. Passing the second floor, still constant velocity. We should start slowing down in just a second as we get to the third floor. Reads less. And we come to a stop, and the door opens.
All right, let's take a look here at a sample problem. A man with mass m stands on a scale in an elevator. If the scale reading is equal to mg when the elevator is at rest, what is the scale reading while the elevator is accelerating downwards with a magnitude of a? Well, if it's going to move downwards, let's set up our axes. Let's call down the positive y direction. And we'll draw our free body diagram for the man in the elevator. We've got a dot for the person. We have the force of gravity on them, mg down, and the normal force, the force of the scale, back up. Now we can draw our Newton's second law equation. Net force, or the sum of all forces, is equal to mass times acceleration. And since we're only worried about this in the y direction, say F net y equals may. Now what I'm going to do is I'm going to go back to my free body diagram, look at all of the forces lined up in the y direction, and replace net force in the y direction with the sum of those forces. So F net y, well, we have mg in the positive y direction, so that will be mg, and Fn in the negative y direction, because we called down positive, just an arbitrary choice. So mg minus the normal force is equal to ma. and that's MAY, but since we're only looking in one direction, we don't have to keep talking about the Y piece. Now all we have to do is solve for the normal force if we want to know what the scale is going to read. So if I take this the next step, normal force is going to be mg minus ma. Or to write it just a little bit differently, normal force is equal to mass times g minus a. So the scale is going to read the person's mass times the acceleration due to gravity minus the acceleration of the elevator. And that should make sense. It's going to be a little less than just mg, because think about it. If you're sitting in an elevator, standing in an elevator, and it's accelerating downwards, then you need to realize that as it's accelerating downwards, you feel lighter for a second. The elevator is accelerating away underneath you. You're going to show up with a smaller weight, a smaller reading on the elevator for a moment or two. Let's take a look at another one. Lizzie stands on a scale in an elevator. If the scale on the elevator reads 600 newtons when Lizzie is riding upward at a constant 4 meters per second, what is the reading on the scale when the elevator is at rest? Well, let's try this one again. We'll draw our free body diagram, and this time let's call up the positive y direction. Again, an arbitrary choice. I usually pick the positive y direction to be a direction that the object moves initially. And if we draw our free body diagram here, there's our dot for Lizzie. We have force of gravity down, mg, and we have the normal force, the force of the scale, back up. We'll write our Newton's second law. Sum of all forces equals mass times acceleration. And we're looking in the y direction here. And then we'll replace F net y again with the sum of all forces in the y direction. Fn will be positive now since we called up the positive y direction. So that's Fn minus mg equals may. But the elevator isn't accelerating. Ay equals 0, so just Fn minus mg equals 0, or the normal force equals mg, the weight. It reads the same thing it would as if they had been still the whole time. Whether it's moving at a constant speed or it's at rest, from a physics perspective, basically it's the same thing. You don't have any change in the scale because the acceleration is 0. The scale is just going to read the person's weight at that point, the force of gravity on them. Let's take a look at a third one here. Davy Dog, with a mass of 25 kilograms, stands on a scale in an elevator when the elevator accelerates upward at 3 meters per second squared. I don't know how they got Davy Dog to sit still on a scale in an elevator. I take my dog to the vet, and it's almost a miracle to get the dog to get on the scale at all, let alone if it was moving. What does the scale read while it's accelerating, and what does it read once the elevator has come to a complete stop? Well, let's walk through this again. Going to move upward, so we'll call that the positive y direction. We'll put in our free body diagram for the dog. We have the normal force up and mg down. So we'll write our Newton's second law equation. Net force in the y direction is equal to may, and we're going to replace F net y with Fn minus mg from our free body diagram. Must be equal to may. Or, solving for normal force equals mg plus may, and if I pull out the m, that's just m times g plus ay. So to solve this for part A, what does the scale read while it's accelerating? Well, the normal force is just going to read the mass, 25 kilograms, times g plus ay. 9.8 meters per second squared. 9.8 meters per second squared plus 3 meters per second squared, which is about 320 newtons. For part B, what does it read once the elevator has come to a complete stop? Well, now normal force is equal to m, still 25 kilograms, times g plus ay, 9.8 meters per second squared, but it's not accelerating, so that's 0. So this is just going to be the weight of the dog, 245 newtons. All right, let's do one last problem. Daffy Duck, with a weight of 230 newtons, which means mg is 230 newtons. Note that that's not his mass. is standing on a scale in an elevator when the elevator accelerates downward at 3 meters per second squared. What does the scale read? Well, let's set up our axis again. We'll call down the positive y direction. That's the direction the elevator moves initially. We'll draw our free body diagram for the situation. There's our duck. We've got the normal force pointed up. We've got gravity down. So net force in the y direction is mass times acceleration in the y direction. Or replacing F net y now with mg minus Fn equals may, or normal force equals mg minus may. So normal force equals, well, mg is 230 newtons minus may. We have to figure out m now. But if we know mg is 230 newtons, that means m is just 230 newtons over g, 9.8 meters per second squared, which is about 23.5 kilograms. So we'll replace m here with 23.5 kilograms multiplied by our a, 3 meters per second squared, which gives us a final answer of right around 160 newtons. All right, hopefully that gets you a good start with elevators as we're talking about dynamics and Newton's laws. If you need more help or are looking for more information, check out aplusphysics.com. Thanks, everyone. Make it a great day.